The background planning methods like value iteration that we have seen in the previous part work well if the state space is not too large. In navigation tasks, for example, there are presumably less than 10 to the 8 intersections of roads in Europe, and value iteration can deal with this on current compute hardware. 10 to the 8 may look like a big number to you, but in fact it is very small if we compare, for example, to the number of possible states that there are in the game of Go, which is on the order of 10 to the 170. Just compare this number, 10 to the 170, to the number of atoms on Earth, which is roughly 10 to the 50. Now, what can we do in these situations where we have so many possible states and also potentially many actions? Let me illustrate this again with a simple toy example that I introduced to you in the previous part. In decision time planning, we do not just update the V and Q values of every state that is connected in this environment, but we start in the state where we actually are, for example here in Lausanne, and we expand the decision tree around the current state. So in Lausanne we can take the actions going to Nice, to Milan or Zurich, and from there on we can iteratively move to the successors of the successors up to a certain depth or until a terminal state is reached. So for example here we have reached already Rome. We don't need to further expand because this is a terminal state, but for Milan and Lausanne there are again multiple possibilities for how we can expand the tree below this node. And when the tree is expanded, this decision time planning tree is expanded, we propagate the values backwards along this decision tree in the very same manner as we did the backward planning before, but this time only along this decision tree. It's like an unrolled version of the full world here that has tree structure, so no loops anymore. So it's very simple and efficient to backpropagate these values at the terminal leaves, or the values in between. And what is also important here to notice is that by starting the decision tree at the node where we currently are in Lausanne, we never will reach, for example, Palermo or Bari. So we never waste compute power to update or compute the values for these two nodes here, because they're never in the search tree beyond the terminal state. Now, in this toy example, the number of actions in each city are still very limited. But for example, in the game of Go, you sometimes have more than 200-300 possible positions where you could place a stone. So expanding the search tree in every position would lead to an explosion of nodes here. So it is very important to have somehow a way not to need to expand the full search tree. Even this is more efficient than doing background planning. Expanding the full search tree is still computationally not possible in many very high dimensional cases. Now for this high dimensional cases, Monte Carlo tree search has proven to be a very effective tool. I illustrate here very briefly how Monte Carlo tree search works. If you want to know more about Monte Carlo tree search, I highly recommend to you to watch this short YouTube video where you see an example of actually running a version of Monte Carlo tree search. So in Monte Carlo tree search, this is specifically for a two-player setting. This graph here, we have white that that can play in this state here. Then we have black to move, then again white to move, then again black to move. Now these numbers here indicate how often out of 21, so 12 times out of 21 simulations that were already run in this Monte Carlo tree search, white won from this position. And these 12 times, they are distributed as follows. By taking this action here, white won 7 games. By taking this action, it won 5 games, and this action, it won 0 games out of 3 that were tried. Now, in Monte Carlo tree search, the first step is to select a branch that is worth further exploring. Now, in this case, because 7 out of 10 games were won in this branch here, it may be interesting to again look at this part of the search tree here. And this is actually what is selected, and here indicated with a thick arrow. So this part of the search tree is selected for an expansion. Now in expansion, one just adds a new node. So this would be some action that black could choose in this state here, which would lead to a new board position where white again could play. Now in the simulation part of Monte Carlo tree search, one actually plays just a purely random game from this start location to the end of a game, until the rules of the game tell you now that the game is over. Now in this example here, where the random game led to a win of black, we backpropagate now this value so that the black won in this setting and not the white. So we have here 0, 1, and now we just update all the numbers along this path that was selected in the first step, and we see here that the numbers 4, 7, 11 and 22 are now the total counts of games that were selected at the different nodes. Now in Monte Carlo tree search, these 4 steps are iterated many times before actually choosing an action. And it is important that the selection does not only happen of actions that are promising because white won many games that were simulated with this random simulation at the end, starting from a position that is below a node of this part of this subtree here. But it is also important that the agent explores sufficiently. So after a while, after having explored here and knowing something about the win probability by taking this action, the agent may move back, or the Monte Carlo tree search may move back to also trying this or that action. And only when it is clear that by searching in these subtrees it is unlikely to win, then the focus shifts again to the more likely parts. Now, how many iterations of these 4 steps are performed before actually choosing an action? That's a hyperparameter that needs to be set. Now, the selection here, I did not really speak much about how we really choose the branch that should be expanded here. And this is really one of the critical parts in Monte Carlo tree search. In this video, you will see a simple method, UCT, to select the branch that should be expanded, or the leaf node that should be expanded. However, to be successful in the game of Go, the researchers that developed AlphaZero modified Monte Carlo tree search in some very important. So for each state action pair, SA, you can think here of SA as the lines out of each node. AlphaZero stores the visit counts, NSA, the total action value, VSA, basically how often a game was won after this state action pair, the mean action value, the QSA, which is divided by the total count, and then the prior action probability, PSA. And that's a very important and new part. So the selection of which action to take at which part in the tree happens in alpha 0 in the following way. So there is the greedy part, which just selects the action A in state st that has the highest action. But the greedy part, the Q value here, is counteracted by the exploration part. And the standard exploration part, we will speak about P later, depends basically just on the visit counts. So what you see here, let us focus first just on this last term here. What you see here is if the count for a certain action in a state st goes up, then because it is in the denominator, the algorithm is less likely to explore further in this direction here. The square root of n of the total visit counts of st basically just counteracts the increasing count here, but not in the same, is not increasing as fast as the linear count for the different actions. So basically this guarantees that one explores the different actions more or less uniformly. Then CS here, this exploration rate, is a factor that increases very slowly with learning, or with the visitation counts. And it actually can be considered almost constant for many settings. Now what is very important is this prior action probability. Now this prior action probability multiplies the standard exploration part to select those actions that are a priori favorable actions, or to not explore directions that are certainly not worth exploring. Let me give a concrete example. You may never have, and fortunately you never will, step in front of a truck that drives at high speed towards you. Our model of the world just tells us it's not a good idea to stand in front of a truck that drives at high speed towards you. So you should never explore this possibility. And this is actually what this prior action probability can do for you. That if you are near a road, then don't step on the road when a truck approaches you. That means that the prior action probability for this action in that state is extremely low. But there may be prior action probabilities for other things that are desirable and worth exploring. And then this factor P here can be large. Now, the important thing is that this factor P, that in a way sets the trade-off between greedy exploration and exploration here, that this one is learned, and that this is learned for the specific environment, for the specific game at hand. We will see later how this prior action probability is learned. It's one of the key innovations of AlphaZero. Then the expansion step in AlphaZero, let me go back to this step here, where we just add, so we run some action here and add a new node in the search tree. In the expansion step, AlphaZero initializes the visit counts for the state action pairs for the total action value and the Q values to 0. And importantly here, it initializes this prior action probability that we just spoke about before to the output, the 8th output of a deep neural network that takes as input the state at this leaf node S that is currently expanded. So this deep neural network that is characterized by neural network weights theta here takes this state, for example, the state of the game of Go, of the board of the game of Go in this state as input, as a visual input, and outputs for all the possible actions for that state, a probability, a prior action probability for the different actions that can be chosen in this state. it also emits a v, a value here, that will be used in the fourth step to come. So AlphaZero does not actually run any simulations. So it's not running a random game up to the end of the game, but instead it uses this v value here that was computed by the neural network. And this v value should really be something like the win probability for that specific state. Now the backpropagation step here, in this backpropagation step, what happens is that, of course, all the visit counts of the state action pairs in the path that was selected in this rollout of Monte Carlo tree search are updated by 1, and here now the value of that was estimated with this neural network enters the backpropagation such that the total action values W get increased by the value that was estimated for this leaf node. And the Q value is nothing else but the total action value divided by the number of visit counts of this state action pair. Yeah, that's just to say again, to repeat again, so the V value, that's what we get here as the output of this neural network. And the other, as I mentioned already before, really important ingredient here is, so this is a vector with all the possible actions in that state, and this vector PA here is the prior action probability that multiplies the exploration part of the in the selection step. Now, after running these 4 steps multiple times, different actions were chosen in the root node. So the S0 is still the state of Go that is in front of the player, and all the state action pairs that were explored during running AlphaZero, they're basically offline, so they were just imagined board states. But for this initial board state from which the agent is planning, the different actions were chosen with different numbers of times according to this greedy and exploration policy. And in the end, the actual action that is taken by the algorithm in this board state S0 is just sampled from a distribution that is given by the counts, the visitation counts of the different actions in this initial state. And here this 1 over tau is a temperature parameter that basically controls how deterministic or stochastic this probability should be. So if this tau goes to very small values, to basically low temperature, then sampling from this distribution becomes more deterministic, whereas it is more stochastic when this tau is still large. Now, how is this neural network actually trained here that is used to compute the prior action probabilities and also to compute the values of the leaf nodes? So the neural network loss is the following one. It is just the outcome of the game, which can be -1 for a loss, 0 for a draw, or 1 for a win, minus the value that was computed for an actually played position, minus the cross entropy loss. So here we want to maximize the probability, the prior action probability. Sorry, we want to maximize the cross entropy such that the prior action probability becomes as close as possible to the actual action that was chosen after running Monte Carlo tree search. So you can think of this prior action probability a bit like the policy in a model free reinforcement learning in policy gradient, for example. And this policy in some way is incomplete, is worse than if one runs Monte Carlo tree search and chooses the action after Monte Carlo tree search. And the reason really is that for these huge action spaces, we don't have ever a good estimate of the true action probabilities for any state. And by just taking a rough estimate of what are good actions and what are bad actions, this helps in the selection process. But then we can improve this these prior action probabilities by really looking at the outcome of a Monte Carlo tree search. And the last factor here is just the regularization of the neural network weights. So you see here that in some way this neural network loss is actually the loss, is like the loss of a standard supervised learning setting, and it is through this Monte Carlo tree search, and in the end also through the fact that AlphaZero just played against itself. So one AlphaZero agent played against another AlphaZero agent, thereby improving the neural network parameters and and by improving the neural network parameters, improving the selection process, and improving the estimate of the win chances, win probability of a certain state in the network. So AlphaZero was a big success, I would say. After some training time here, they could show that AlphaZero can beat Stockfish. Stockfish is one of the best chess playing engines in the world. So it's better than, well, yeah, state-of-the-art chess engine. It's also better than a state-of-the-art shogi engine, Elmo. And AlphaZero also reached higher levels than the algorithm that AlphaGo Lee, that was the one that was used to beat the world champion in Go. And it is even better than AlphaGo Zero, which was a version of AlphaGo that was still specifically designed for Go and not for any game, because here it's really the same algorithm that is applied to the different games. And only what is different between the different games is how the board positions are given as input to the neural network. So to summarize this part, in each position of the game for both players, Monte Carlo tree search runs for some time. The subtree below the actual next state is retained as the initial Monte Carlo tree search tree for the next iteration. That's an important step that I didn't mention before, but we can reuse that part of the Monte Carlo tree search tree that is actually that the agent actually transitions to. All the other branches we can neglect for the rest of the game, but we can reuse that part of the Monte Carlo tree search. In contrast to traditional Go, chess, and shogi software, there is absolutely no handcrafting of promising tree expansions. So this is something that was kind of needed before, or position evaluations, because the selection of Monte Carlo tree search is focused on promising actions through these learned prior action probabilities P, and the value of the leaf nodes is based on a learned position evaluation function. So both this prior action probability that expands the tree in promising directions and the evaluation of each board position V are learned by the algorithm. The prior action probabilities P are trained with a cross entropy loss to match the actual policy of Monte Carlo tree search, which is always a tiny bit better because you look a little bit ahead instead of just taking instead of just taking a probability that is never perfect for an action probability that is never perfect, because we cannot play infinitely many or almost infinitely many Go games. And the values V are trained with a squared error loss to to the actual outcomes C of the game. AlphaZero does not need to learn the reward and the transition model, R and P, because Monte Carlo tree search here relies really on the hard-coded rules of the game. And the key question really is, what if the model is unknown, which will be discussed in the next part.